It was the size of a star, but it was not a star. It was brighter than 1 trillion suns, brighter than 100 billion stars burning together in a single galaxy. It was so bright that a man at a telescope in California in 1963 looked at it and could not explain what he was seeing and had to sit down. It was 2.5 billion light years away, and it was the smallest thing that had ever been that bright. Something is eating. Something at the center of an ancient galaxy is pulling gas and dust and shredded stars into a spiral, compressing them, heating them past any temperature that exists naturally anywhere in the universe, and releasing that energy outward in every direction at once. Light, X-rays, radio waves, a column of plasma moving at 99.9% the speed of light, punching through the surrounding galaxy for millions of light years. This has been happening since before the Earth existed. You are going there tonight. The object you are traveling toward is called 3C 273. It sits in the constellation Virgo. It is 2 billion light years away. On a very dark night, with a sufficiently large amateur telescope, you can see it, a faint point of light, indistinguishable from a distant star. But it is not a star, it is a galaxy, and at the center of that galaxy, a black hole with a mass of nearly 900 million suns is consuming matter at a rate that releases more energy every second than our entire Milky Way produces in a year. When the light you are seeing left that object, Earth's oceans held nothing more complex than single-celled organisms. That light has been traveling toward you for 2 billion years. Tonight, you travel back. At the center of the disk, temperatures reach 100 million degrees, hotter than the core of the sun, hotter than the moment of a nuclear detonation by a factor of thousands. The X-rays produced there could pass through a meter of solid lead without slowing. You will go closer than that. A jet of plasma is already forming. It begins at the black hole's poles, threaded along magnetic field lines, so tightly coiled that they extract energy from the spin of space-time itself. The plasma exits at a fraction below the speed of light and does not stop for 3 million light years. It is longer than the distance between us and the Andromeda galaxy. Tonight you will stand inside it. There is a place where time runs slower than it does here, where a clock placed 1 kilometer closer to the center ticks measurably behind a clock placed 1 kilometer farther out, where the light produced at the innermost edge of the disk loses energy just climbing away from it, stretched by gravity into longer wavelengths before it even begins its 2 billion year journey through the dark, where space-time itself is being dragged in circles by the rotation of a black hole, like water circling a drain, except the drain is 900 million times the mass of the sun, and the water is the fabric of the universe. You will be at that place tonight. You will watch gas cross the last stable orbit. You will watch it disappear. There is also a question that nobody has fully answered. How did something that massive form so quickly? The universe was less than 2 billion years old when 3C 273's black hole had already reached 900 million solar masses. The physics of how that happened, the seed, the growth rate, the mechanism, is still contested, still open, still one of the genuine mysteries sitting at the center of modern cosmology. Tonight you will be inside that mystery. In the year 1963, a Dutch-American astronomer in California looked at a spectrum and could not read it. The lines were wrong in a way that should have been impossible. Nothing in physics had accounted for what he was seeing. Tonight, you will understand what he understood. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research and observation. Just relax and feel free to let this play as you drift off to sleep. Now imagine, for most of human history, the sky above us held a mystery we did not know was there. Among the stars, fixed, familiar, the same constellations drawn by every civilization that ever mapped the night, there were points of light that were not stars. They appeared stellar. They were point sources, unresolved by any telescope, with no visible disk, no halo, no galaxy surrounding them. Early radio surveys of the sky cataloged them as radio sources. The third Cambridge catalog, 3C, listed them by number: 3C 273, 3C 48, compact, bright, puzzling. For years, astronomers debated what they were. They were too small to be galaxies. They were too bright to be stars. Some assumed they were nearby objects of unknown type. The idea that they could be distant was dismissed. Nothing at cosmological distances could be that luminous. The universe's power budget, as physicists understood it in the late 1950s, did not have room for objects that bright. Then Martin Schmidt measured 3C 273, and the universe turned out to be larger and stranger and more violent than anyone had calculated. The word quasar was coined almost immediately, quasi-stellar radio source, a name built from confusion. We do not know what this is, so we will describe only what it appears to be. A star-like thing that emits radio waves. The name persisted long after the confusion was resolved, the way emergency names sometimes outlast the emergency. What Martin Schmidt had found, what he and his colleague Jesse Greenstein had confirmed that afternoon in Pasadena, was a black hole in the act of eating. Not a quiet black hole, not the dormant kind, like the one at the center of our own galaxy, sitting still in the dark, pulling in almost nothing, radiating almost nothing, patient in the way that objects with no metabolism are patient. This was the other kind. You are 2.4 billion light years from Earth. The number is worth sitting with, not rushing past. The light that will carry images of you, if any were produced, will not reach Earth until the year 2,400,000,000,2026. Long after the sun has expanded into a red giant, long after the oceans have evaporated, long after anything that could receive a signal exists on that planet. You are, in any practical sense, alone. The galaxy around you is not the Milky Way. It is an elliptical galaxy, a system of several hundred billion stars, arranged not in the flat disk and spiral arms you would see from Earth's neighborhood, but in a smooth, three-dimensional ellipse, a loose cloud of stars rotating slowly around a common center. The stars here are older, on average, than the stars in our galaxy. Many of them formed in the universe's first few billion years, when gas was dense and star formation was rapid and chaotic. And at the center of this galaxy, there is something that was not here when those stars formed. Or rather, something that was always here, but that recently woke up. You begin to feel it before you see it. Not in the way you feel warmth from a fire, not thermal radiation, At this distance, measured in tens of thousands of light years from the galactic center, the energy density is not yet extreme. What you feel, or what some instrument calibrated to your perception would register, is a directional pressure. Light has momentum. This is not a metaphor or a poetic description. It is a measurable physical fact. Photons carry momentum proportional to their energy, and when they strike a surface, any surface, including the hypothetical surface of a spacesuit, including the hypothetical surface of your skin, they exert a force. On Earth, this force is so small as to be irrelevant. In the immediate vicinity of a quasar, it is not irrelevant. Radiation pressure from 3C273 at its peak luminosity exceeds the Eddington limit for any stellar object. The Eddington luminosity is the theoretical maximum brightness at which radiation pressure outward equals the gravitational force inward, the point at which an object would blow itself apart if it radiated any more. Quasars routinely approach or exceed this limit, which means the system is operating at the edge of its own self-destruction, balanced in a state that should not persist, sustained by the continuous inflow of new material. You are moving toward the source of that pressure. The galaxy thickens around you as you approach its center. The star density increases from the sparse interstellar distances of the outer disk to something more crowded, stars separated by light months rather than light years. The interstellar medium, the thin gas between the stars, also changes. In the outer galaxy, it is cold, diffuse, mostly neutral hydrogen drifting in wisps and filaments. Here, approaching the nucleus, it becomes warmer, ionized, disturbed by the radiation pouring outward from the center. The gas is not calm. You can read the energy state of hydrogen by the photons it emits and absorbs. Cold hydrogen emits at 21 centimeters, the famous hyperfine transition, the wavelength used by astronomers to map the structure of galaxies. But this hydrogen is not cold. It is emitting in the ultraviolet. It is losing electrons. It is being stripped by the radiation pressure of whatever is at the center, the way paint is stripped by a high-pressure hose. You are 50,000 light years from the nucleus. Still an enormous distance, the light from the active center, which arrives here with enough energy to ionize gas, left the accretion disk 50,000 years ago. You are not seeing what the quasar is doing now. You are seeing what it was doing 50,000 years ago. This is one of the stranger features of existence at cosmological scales. Causality, the requirement that effects follow causes, means that information travels no faster than light. The quasar at the center of this galaxy is not a single moment. It is a history distributed across space. The closer you are to it, the more recent the information you receive. You are moving toward the present. At 10,000 light years from the center, something changes in the visual field. The galactic nucleus is no longer a bright point indistinguishable from a particularly luminous star cluster. It has structure, not the structure you would see in a nearby galaxy. No fine spiral arms, no distinct molecular cloud complexes, no individual star-forming regions you can resolve. The structure here is different, broader, less organized. A diffuse central brightness that increases continuously toward the core, punctuated by a region of extreme luminosity that the eye, or its instrument analog, cannot resolve even at this distance. That unresolvable point is the accretion disk. The disk itself is only a few light days across. At this distance of 10,000 light years, Resolving an object a few light days wide would require an angular resolution far beyond any telescope ever built. But you are not observing it through a telescope. You are here, and you are still 10,000 light years away. The energy output of 3C273 at peak activity has been measured at approximately 4 × 10 circumflex 39 watts. This is a number that has no human scale referent. A nuclear weapon produces roughly 10 circumflex 15 joules of energy in its detonation, call it 10 circumflex 22 watts, at the moment of maximum output for a fraction of a second. The quasar sustains 410 circumflex 39 watts continuously. It is 100 trillion times more powerful than a hydrogen bomb running without interruption for millions of years. The energy comes from gravity. Not fusion, not fission, not chemical combustion. Gravity, the conversion of gravitational potential energy into radiation as matter falls toward the event horizon. The efficiency of this process, the fraction of the infalling matter's mass energy that is converted to radiation before it crosses the horizon, is approximately 6% for a non-rotating black hole and up to 42% for a maximally rotating Kerr black hole. For comparison, nuclear fusion, the process that powers every star in the universe, converts approximately 0.7% of mass to energy. Gravity at the edge of a black hole is 60 times more efficient than the core of the sun. This is why quasars exist. This is why they are so bright. This is why Martin Schmidt in 1963 looked at his spectral data and had to sit down. The universe had found a way to be more violent than physics had budgeted for. You continue inward. At 1,000 light years from the center, the radiation environment has changed substantially. The ultraviolet flux, the high-energy photons streaming outward from the disk, is intense enough that any unshielded organic molecule would be destroyed within seconds. The gas around you is fully ionized. There are no neutral atoms. There is only plasma, electrons separated from their nuclei, moving freely through the intense electromagnetic fields that thread this entire region. The magnetic field here is not like Earth's magnetic field, gentle and stable and navigated by compass needles. This field fluctuates, it twists, it reconnects, field lines from different directions meeting, canceling, releasing stored magnetic energy as bursts of acceleration that drive charged particles to relativistic speeds in fractions of a second. The region is noisy in the electromagnetic sense, every frequency: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. The quasar does not emit at one wavelength the way a star peaks at a particular color determined by its temperature. It emits across the entire spectrum through multiple distinct physical processes happening simultaneously in different regions of the accretion disk. You are close enough now to begin to see it as a structure rather than a point. The disk is a faint smear of light at first, not the luminous ring you might imagine from diagrams. The brightness is not uniform. The inner edge, where material is falling fastest and temperatures are highest, is the most luminous. The outer edge is cooler, dimmer, more extended. The whole structure rotates. Not like a rigid wheel, like a fluid, the inner edge completing an orbit in days, the outer edge completing an orbit in decades. This differential rotation is critical. It is what generates the magnetic field structure that drives the turbulence, and the turbulence is what drives the accretion. Without differential rotation, the disk would not heat. Without heating, the gas would not radiate. Without radiation, there would be no quasar. The black hole at the center is not the brightest part. The black hole at the center produces no light at all. The brightness you are approaching, this extraordinary galaxy outshining luminosity, is produced entirely by the gas just outside the event horizon in the last moments before it falls in. The black hole itself is dark. It is surrounded by the brightest thing in the observable universe, and it contributes nothing to that brightness except its gravity. You are descending now. The outer edge of the disk is perhaps 2 light days from the center. You cross it slowly, watching the plasma around you thicken. The temperature at this radius, measured in tens of millions of kilometers from the event horizon, is in the tens of thousands of Kelvin. Hot enough to vaporize any material object. Hot enough that the dominant radiation is ultraviolet, the same radiation that ionized the gas 1,000 light years behind you. But this is still the cool edge. The disk narrows inward, the gas spirals. It does not fall straight down. Angular momentum, the same property that keeps planets in orbit, keeps the gas from collapsing directly inward. Instead, it spirals, losing angular momentum incrementally through magnetic friction, each orbit bringing it slightly closer to the center, each orbit slightly faster than the last. You follow the spiral. The temperature climbs. At a distance of 100 gravitational radii from the black hole, a unit defined by the mass of the black hole itself, approximately 1 gravitational radius for every solar mass, meaning here for a 900 million solar mass black hole, 1 gravitational radius equals about 1.3 billion kilometers. The temperature has climbed to several million Kelvin. The dominant radiation is now X-ray. The gas is no longer behaving like gas in any familiar sense. It is a magnetized plasma in which individual particle interactions are less important than the collective behavior of the electromagnetic field. The electrons and ions move in response to the field, and the field moves in response to the electrons and ions, and the whole system evolves in ways that can only be described by magnetohydrodynamics, the physics of conducting fluids in magnetic fields. It is one of the most mathematically complex environments in nature, and you are inside it. The light around you is no longer white. It never was white, but your perception of it has shifted as the spectrum has shifted. The peak emission has moved through ultraviolet and into soft X-ray. If your eyes could respond to X-rays, the disk would appear uniformly, blisteringly bright. Since they cannot, the visible component of the emission, the portion of the spectrum that overlaps with human vision, is a deep saturated blue, the blue of the hottest visible light-emitting plasma. The center is blue-white, and it is approaching. You are 30 gravitational radii out. The curvature of space-time is measurable now, not as a sensation of falling, but as a measurable deviation in the path of light around you. Photons from the far side of the disk, which should be invisible behind the black hole, appear at the edges of your visual field, bent around the gravitational curvature of the central mass. The disk, which should look like an ellipse foreshortened by your viewing angle, appears warped, one side brighter than the other, an effect of the Doppler shift as the near edge of the disk moves toward you and the far edge moves away. This is not a visual effect. This is general relativity, operating on the structure of space-time, visible to any observer in this location. You are close enough now to see the shadow. The black hole casts no shadow in any conventional sense. Shadows require a light source casting from behind an object, but there is a region at the center of the disk that is darker than its surroundings. The event horizon itself, the mathematical surface beyond which light cannot escape, is invisible. What you can see is the photon sphere, the radius at which light orbits the black hole, captured into closed loops, forming a bright ring around the dark central region where no light escapes. This is what the Event Horizon Telescope imaged when it photographed M87 asterisk in 2019 and Sagittarius A asterisk in 2022. You are seeing the same structure from within the accretion disk at a distance no telescope will ever achieve. The last stable orbit is ahead. The innermost stable circular orbit, the equazo, is the closest distance at which matter can orbit the black hole without inevitably spiraling inward. For a non-rotating Schwarzschild black hole, it sits at 3 times the Schwarzschild radius. For a maximally rotating Kerr black hole, it can shrink to nearly the event horizon itself. The black hole at the center of 3C273 is rotating. All black holes that have accreted material are rotating. Angular momentum is conserved, and the infalling gas carries angular momentum that is transferred to the black hole over millions of years of accretion. The spin of this black hole is not known precisely, but based on the luminosity and the inferred accretion rate, it is rotating at a significant fraction of the maximum possible spin, which means the ISCO is close to the horizon, which means the disk extends deeper than it would around a slower spinning black hole, which means more of the gravitational energy is extracted before the gas crosses the point of no return. You hover at the ISCO. The gas that was beside you a moment ago, the plasma you were moving through, the ions and electrons in their magnetized spiral, has crossed this boundary. It is now falling. There is no orbit below this radius that is stable. Every circular or elliptical path inside this boundary is a decaying path, a trajectory that ends at the event horizon in a finite proper time. The gas does not fall slowly. From the NISCO, the infall to the event horizon takes, in the reference frame of the infalling material, a very short time. In your reference frame, hovering outside, watching, the gas appears to slow as it approaches the horizon, redshifting into longer and longer wavelengths, dimming, never quite reaching the surface you are watching. This is the Schwarzschild geometry. Time runs differently here. Not metaphorically, not in the sense of time feeling slower, in the sense that a clock placed at your current position, hovering at the ISCO, ticks measurably slower than a clock placed far from the black hole. The gravitational redshift, the loss of energy by photons climbing out of a gravitational well, is the visible expression of this time dilation. The photons produced in the inner disk carry the signature of this slower clock. Their wavelengths are stretched before they even begin their journey across the galaxy. The light that reaches Earth from 3C273 carries, encoded in its spectrum, the signature of time running slowly at the edge of a 900 million solar mass black hole. Martin Schmidt's spectral lines were not just redshifted by the expansion of the universe. They were redshifted by gravity. Both effects layered on top of each other. You remain at the boundary. Above you, in the direction opposite the black hole, the disk continues outward, the temperature gradient reversing, the plasma cooling, the dominant radiation shifting back toward ultraviolet, and then visible, and then infrared as you move your gaze outward. At the poles, something different is happening. The magnetic field lines, which have been threading through the disk and tangling in the turbulence, are doing something else at the rotational axis. They are collimating. They are being wound by the frame dragging of the rotating black hole, the effect predicted by general relativity, in which a massive rotating object drags the surrounding space-time along with its rotation, like a spinning ball submerged in honey, dragging the honey around it. The field lines, wound tight by this dragging, are threading the event horizon itself. Energy is being extracted from the spin of the black hole. Not matter, not radiation from inside the horizon. Nothing crosses outward through the event horizon, but the rotational energy of space-time itself, stored in the ergosphere of a Kerr black hole, the region outside the horizon where space-time is dragged so violently that nothing can remain stationary. This energy can be tapped. The mechanism is called the Blandford-Znajek process. It works by threading magnetic field lines through the ergosphere, which spins those field lines, which accelerates charges along the field, which launches plasma outward along the rotational axis at relativistic speeds. The jet is forming above you. Right now, in this moment, looking up along the rotational axis of the accretion disk, you can see the beginning of it, a column of plasma tightly collimated by the magnetic field, moving outward from the poles at greater than 99% of the speed of light. It has already been traveling for 3 million light years. It is still accelerating. You have been here long enough to feel the scale of what this place is. Not a violent explosion, not the sudden detonation of a supernova, which releases its energy in seconds or hours and fades. This is sustained. This has been running for tens of millions of years. The disk will continue to feed as long as there is gas in the host galaxy to funnel inward. The jet will continue to push as long as the disk feeds. The radiation will continue to stream outward across 2 billion light years of space until it reaches a small blue planet where a man at a telescope will hold a spectrum up to the light and not be able to read it. The universe has been operating on this scale the entire time. You just did not know where to look. Slowly, you begin to move outward. Not quickly. There is no urgency here. The accretion disk will not change appreciably in the time it takes you to drift back toward the outer regions of the disk. This is geological time, astronomical time, the time that stars measure their lifespans in. The plasma around you cools by degrees as you move away from the inner edge. The X-ray flux diminishes. The blue-white fades towards something softer, still blue, still intensely luminous, but no longer the blinding extreme of the inner disk. You pass through the region where the ultraviolet dominates, where the gas is fully ionized but no longer at the most extreme temperatures, where the magnetic turbulence is still present but less violent, where the spiraling motion of the plasma has a rhythm you can almost follow, a slow, vast clockwise rotation when viewed from above the disk plane, each orbit measured not in minutes but in years. The outer edge of the disk is behind you now. Ahead of you is the broader structure of the quasar's influence zone, the region of the host galaxy that has been transformed by the presence of this active nucleus, the gas that has been ionized, the molecular clouds that have been disrupted, the star-forming regions that have been shut down by the radiation pressure and the jet. A quasar does not only consume, it also shapes everything around it. And the story of that shaping, the story of how this single object at the center of a galaxy can determine the fate of hundreds of billions of stars, is where you are going next. The jet stretches ahead of you into the dark. 3 million light-years of accelerating plasma threading through the halo of the host galaxy and beyond into the intergalactic medium, carrying the energy of a spinning black hole outward into space. You follow it into the quiet. The cosmic web is not uniform. This is the first thing that becomes clear as you pull back to a scale large enough to see it whole. The universe does not distribute its matter evenly. In the early universe, in the first few 100 million years after the Big Bang, the matter that existed was almost uniform, almost perfectly smooth. But almost is not perfectly. There were fluctuations, regions where the density was slightly higher than average, and regions where it was slightly lower. Gravity amplified those fluctuations. Higher density regions pulled in more matter from surrounding lower density regions. As they grew denser, they pulled harder. The lower density regions grew emptier. Over hundreds of millions of years, this process of gravitational amplification converted the nearly smooth early universe into the highly structured one you are currently traversing, a web of filaments and sheets and nodes with vast voids between them where almost nothing lives. The filaments are where the gas lives. Hydrogen and helium, the primordial composition of the universe, stream along these filaments under gravity, flowing toward the nodes, the densest intersections of the web, where massive dark matter halos have concentrated enough baryonic matter to form the first galaxies. The first galaxies were not like the Milky Way. They were smaller, less organized, more gas-rich, more actively star-forming. The universe in its first billion years was converting its available hydrogen into stars at a rate far higher than it does today, almost frantic by cosmic standards. Dense molecular clouds collapsing, new stars igniting, the most massive of them living only a few million years before exploding as supernovae, enriching the surrounding gas with heavy elements forged in their cores. And in some of these early galaxies, perhaps in many of them, the process of black hole formation was also underway. How the first supermassive black holes formed is one of the most contested questions in modern astrophysics. The problem is one of time. The black hole at the center of 3C 273 has a mass of approximately 900 million solar masses. At the time this quasar was active, roughly 2 billion years into the universe's history, this black hole already had that mass, which means it had to accumulate 900 million solar masses of material in 2 billion years. That is not impossible. If a seed black hole, perhaps the remnant of the first generation of massive stars, stars that could form in the metal-free early universe and grow to hundreds of solar masses before collapsing, began accreting at the Eddington limit continuously from very early times, it could in principle grow to this mass. But continuous Eddington-limited accretion for billions of years is an extreme condition. It requires a constant supply of infalling gas. It requires that the radiation produced by the accretion not blow the surrounding gas away before it falls in. It requires a complex balance between feeding and feedback that must be maintained without interruption. When astronomers find quasars at the highest redshifts, the most distant, the earliest, the problem becomes more acute. J0313 1806, the most distant quasar currently known, hosts a black hole with a mass of 1.6 billion solar masses. It was observed as it was when the universe was only 670 million years old. 670 million years is an extremely short time to grow a black hole to 1.6 billion solar masses, even under the most favorable conditions currently understood. Some models invoke direct collapse black holes, scenarios in which entire gas clouds, instead of fragmenting into stars, collapse directly into a single massive object with an initial mass of perhaps 100,000 solar masses, bypassing the stellar evolution stage entirely. These seeds would be far more massive than stellar remnants and could grow to supermassive scales more quickly. These models are consistent with the observations, but they have not been confirmed. The origin of the first supermassive black holes remains one of the genuinely open questions in cosmology. You are inside that question. You are 2 billion light years from Earth, inside a galaxy hosted by one of those black holes, and the mechanism by which it got here, by which it grew from whatever seed existed in the early universe to the 900 million solar mass object currently generating the accretion disk behind you, is not fully understood. This is not a failure of science. This is science in progress. The observations exist, the data from high redshift quasar surveys, from X-ray telescopes, from the James Webb Space Telescope observing the earliest galaxies, from radio arrays mapping the jets and lobes of distant AGN. All of this exists, and it is constraining the models, narrowing the possibilities, closing in on an answer that is not yet closed. The universe keeps its early history partially encrypted. We are working on the key. Farther along the filament that you are following, farther from the node where this galaxy sits, deeper into the web, other galaxies are visible. Some of them are also active. Some of their nuclei are also glowing, also driving jets, also pouring radiation outward into the intergalactic medium. The quasar era, at this epoch of the universe, is not a rare phenomenon. It is the dominant mode of black hole behavior. In the universe as it exists at your home time, in the contemporary universe, 13.8 billion years after the Big Bang, active galactic nuclei exist, but they are comparatively rare. Most massive galaxies host supermassive black holes at their centers, but most of those black holes are in a low accretion state. They are accreting at a tiny fraction of their Eddington luminosity. Their disks, if they exist at all, are geometrically thick and radiatively inefficient. Their jets, if they exist, are low power compared to the classical radio jets of the quasar era. The universe has quieted. This quieting is itself a consequence of the quasar activity. The jets and radiation of the quasar era heated the intergalactic medium. They deposited energy into the gas that might otherwise have cooled, condensed, and fallen into galaxies to fuel further star formation and further accretion. They enriched that gas with the heavy elements produced in the star-forming regions. They compressed and triggered, and then disrupted. The universe's gas supply, viewed at the largest scales, was transformed by billions of years of AGN activity. Less gas available to fall into galaxies. Less gas available to feed central black holes. Fewer active nuclei. quieter galaxies, a quieter universe. The process is not complete. AGN activity still occurs and will continue to occur wherever sufficient gas supply exists to trigger an active phase. Galaxy mergers, which can drive large quantities of gas toward galaxy centers, are still happening, and many of them trigger brief periods of quasar-level activity before the system settles. But the era of maximum quasar activity, the era you are currently inside, is past. From the perspective of 13.8 billion years in the future, this moment is the brightest moment, the loudest moment, the most energetically active moment in the universe's history. And you are here for it. The filaments around you glow faintly in the deep ultraviolet, the signature of gas ionized by the collective radiation of the quasars distributed throughout this era of the cosmos. The epoch of reionization, when the first quasars and the first galaxies flooded the universe with ultraviolet photons and converted the neutral hydrogen of the post-recombination universe into the ionized plasma that has persisted ever since, has already occurred by this point in cosmic history. The universe was once opaque, a sea of neutral hydrogen, atoms that absorbed ultraviolet photons before they could travel any significant distance. In that universe, no quasar could be seen from afar. The light was trapped. The universe was a fog. The first massive stars and the first quasars burned through that fog. Bubble by bubble, the neutral hydrogen was ionized. The bubbles grew and merged. By roughly 1 billion years after the Big Bang, the process was largely complete. The universe became transparent, and all the light that had been trapped, all the radiation produced by those first stars and black holes, was suddenly free to travel. You are in that transparent universe now. You can see across 2 billion light years because the hydrogen between here and there is ionized, because quasars like this one and the galaxies around them converted the neutral medium into plasma. The light you are traveling through tonight was made possible by this violence. Everything is connected in this way. The transparency of the universe, the very fact that starlight can travel from distant galaxies to arrive at a planet where beings evolved to look up and wonder, is a consequence of the most energetic phase of the universe's history. The quasar era did not only shape galaxies, it shaped the medium through which the universe is visible. You breathe in the dark between galaxies. Not literal breath, there is nothing here to breathe, but the rhythm of it, the pace. The filament you are following curves gently in the dark. The node ahead, another galaxy cluster, another concentration of dark matter and baryons, another assembly of galaxies working through their formation and merging in evolution, is 80 million light years away. A long way, but not as long as where you have been. The quasar behind you, 3C273, the object Martin Schmidt stared at in Pasadena in 1963, the object he spent years measuring and calculating and finally publishing a single remarkable paragraph about in Nature, is still blazing. It will blaze for millions of years more before its gas supply begins to thin. And then, slowly over timescales that make human history vanish into rounding error, it will quiet. The accretion rate will fall, the disk will cool, the jet will weaken. The blinding luminosity that outshines hundreds of billions of stars will fade to a gentler glow, then to a faint active nucleus, then to nothing visible without the most sensitive instruments. The galaxy will remain. The black hole will remain. And 2 billion light years away, on a small planet that does not yet exist, a species that has not yet evolved will one day point a telescope at the place where the quasar was and see a faint, ordinary-looking elliptical galaxy, and only the most careful measurements of its central region will reveal that something extraordinary happened there, once, long ago. The gravity of what it was, still present, still measurable, still real. You are drifting now. Not toward anything in particular, just outward, along the filament, through the dark, in the direction of the void that separates this node of the cosmic web from the next. The void is large. Hundreds of millions of light years of nearly empty space, the dark matter skeleton of the universe running through it as invisible scaffolding, a few stray galaxies scattered at its edges where the filament's thin. There is nothing here to name, just space. Just the faint hiss of the cosmic microwave background, the relic radiation of the Big Bang itself, cooled by the expansion of the universe from the fierce heat of the early cosmos to a temperature of 2.725 Kelvin, filling all of space, arriving from every direction, a whisper of the universe's origin, still audible in every corner of what exists. It reaches you here. It reaches you wherever you are. The universe began 13.8 billion years ago, and it is still announcing itself. You listen to it in the dark between galaxies, and the listening feels like something that does not need a name. The breath slows. The vast distances do not diminish what you are. They do not make you smaller than you were before you understood them. They make you a part of something that has been going on since before the Earth was made, that will continue long after the sun is cooled, that has no particular concern for the passage of time, because time is simply the medium through which it operates. The quasar is behind you. The void is around you. And somewhere ahead, in the deeper history of the universe, in the first ignition of the first active black holes, in the beginning of the era that made the cosmos what it became, the next part of this story is waiting. You close your eyes. The cosmic microwave background hums at 2.725 Kelvin, as it has since the universe was 380,000 years old. And you drift. The universe is getting younger around you. This is not a figure of speech. You are traveling backward in time, not in the science fiction sense of reversing a clock, but in the only sense that travel across cosmological distances actually permits. Light travels at a finite speed. Every photon you receive from a distant object carries information about that object as it was when the photon departed. The further away the source, the older the information. When you travel toward a distant source, the light you encounter along the way has been traveling longer, carries older information, shows you an earlier state of the universe. You are now far enough from your starting point, far enough from the 2 billion light-year distance of 3C273, moving deeper into the past, that the universe around you is measurably different. The galaxies are younger, smaller, less organized. The spiral structures that will eventually develop in disk galaxies have not yet fully wound. The elliptical galaxies that dominate the most massive halos are still assembling through mergers, their smooth profiles not yet stabilized. The interstellar medium within each galaxy is more gas-rich. The conversion of hydrogen into stars and then into stellar remnants has been underway for only a few billion years, not the 10 or 12 billion years that will have elapsed by the time a species on a small rocky planet begins pointing telescopes at the sky. The universe at this epoch has not yet used most of its available star-forming material. It is a younger universe in the way that a forest is younger before the great trees have grown, not empty, not quiet, but dense with potential, its resources not yet committed to their final forms. And everywhere you look, the centers of galaxies are bright. This is the quasar era. Not a single event, not a phase that began on a particular date and ended on another. A broad epoch spanning roughly from 1 billion to 4 billion years after the Big Bang, with a peak around 2 to 3 billion years in, during which the fraction of massive galaxies hosting actively accreting black holes was far higher than it is in the contemporary universe. The sky at this epoch, if you could see it in its entirety, would be populated with quasars in every direction. Hundreds of thousands of them at various distances, various luminosities, various stages of their active phases. You are traveling toward the brightest period of the universe's history. The redshift is climbing as you move. Redshift is the astronomer's measure of cosmological distance and look-back time, the stretching of light's wavelength by the expansion of space during the time the light was traveling. At redshift 0, you are in the contemporary universe. At redshift 1, you are seeing the universe as it was roughly 8 billion years ago. At redshift 2, roughly 10 billion years ago. At redshift 6, the edge of the epoch of reionization, where the universe was still partially opaque, you are looking at the universe as it was roughly 12.5 billion years ago, when it was less than a billion years old. You are currently at approximately redshift 3. The universe is about 2 billion years old around you, and the quasar density, the number of active galactic nuclei per unit volume of space, is approaching its historical maximum. The galaxy you are entering is smaller than the host galaxy of 3C 273. Its stellar mass is perhaps 50 billion solar masses, roughly half the mass of the Milky Way as it exists today. It is a disk galaxy, loosely organized, with irregular spiral structure being disrupted by an ongoing minor merger. A smaller satellite galaxy, perhaps 2 billion solar masses, currently passing through the outer disk of the larger system on a trajectory that will bring it through the center in approximately 400 million years. The merger is what triggered the current active phase. Galaxy mergers are among the most reliable triggers of AGN activity. The gravitational interaction between two merging systems drives gas inward through tidal torques. The differential gravitational force across an extended object causes its rotation to become disordered, removing angular momentum from large quantities of gas and allowing it to fall toward the galactic center. The infalling gas finds the central black hole and begins to accrete. The black hole in this galaxy is smaller than the one in 3C 273. Its mass is approximately 200 million solar masses, but it is accreting at a high rate, close to its Eddington limit, and at these accretion rates, a 200 million solar mass black hole is extraordinarily luminous. The AGN at the center of this galaxy outshines its host by a factor of several hundred. You have seen this before. The geometry is familiar: the accretion disk, the jets, the ionized gas extending through the host galaxy, the radio lobes forming at the jet termination points in the intergalactic medium beyond the galaxy's edge. But the context is different. Around 3C273, the intergalactic medium was already ionized, already transparent, already the product of billions of years of quasar and stellar ultraviolet radiation. Here, in this earlier universe, the reionization process is still underway at the largest scales. The great voids between the filaments of the cosmic web are not yet fully ionized. Pockets of neutral hydrogen still persist in the least dense regions of the universe, the last remnants of the opaque era. The quasar you are approaching is one of the objects helping to complete the reionization. Its ultraviolet radiation streams outward in a sphere, an ionized bubble called a Stromgren sphere in the context of individual stars, but operating here on a galactic scale, extending hundreds of millions of light years from the nucleus. Within that bubble, the hydrogen is ionized. Beyond its edge, the hydrogen is neutral. You are inside the bubble. You can see further here than you could outside it. The boundary of the bubble is a wall of opacity. The neutral hydrogen scatters and absorbs the ultraviolet photons that would otherwise carry information from beyond the boundary. If you were outside the bubble, the view in the ultraviolet would terminate at the wall. Inside the bubble, the ionized medium is transparent, and you can see across it to the quasar at its center. The quasar at the center of this bubble is not the brightest object in the universe. There are brighter ones at this epoch. Some of the most luminous quasars known, objects that will be discovered by human astronomers billions of years in the future, cataloged in surveys conducted with telescopes that do not yet exist, studied by people who have not yet been born on a planet that has not yet formed its continents. Those objects exist at approximately this epoch of the universe. SDSS J1030 plus 0524. Redshift 6.3, observed when the universe was approximately 900 million years old. A black hole of approximately 1 billion solar masses, already assembled, already active. ULSJ 1120 plus 0641. Redshift 7.085. The universe was approximately 770 million years old. A black hole of approximately 2 billion solar masses. J031 31806. Redshift 7.64. The universe was approximately 670 million years old. A black hole of 1.6 billion solar masses. Each of these objects represents an extreme, a black hole that grew faster than standard models of accretion easily allow, in a universe that had not yet had enough time for the growth to proceed by ordinary means. The question their existence poses is not merely academic. If these black holes, objects of 1 to 2 billion solar masses, existed when the universe was less than 700 million years old, then the seeds from which they grew must have formed extremely early and grown extremely fast. The standard picture of a stellar mass black hole, perhaps 10 to 100 solar masses, the remnant of a massive star, accreting continuously at the Eddington limit, does not produce a 2 billion solar mass black hole in 700 million years. The math does not close. Not quite. There are margins in the calculation. If accretion occasionally exceeds the Eddington limit, a condition called super-Eddington accretion, which is theoretically possible and has been observed in smaller systems, the growth rate increases. If the seed black holes were more massive than stellar remnants, if direct collapse black holes formed in the early universe, with initial masses of perhaps 100,000 solar masses, the required growth factor decreases substantially. Both mechanisms may have operated. Neither has been directly observed in the early universe. The James Webb Space Telescope, operational since 2022, is designed in part to address this question. Its infrared sensitivity allows it to observe the first galaxies and the first active galactic nuclei at redshifts beyond 7, further back in time than any previous facility. The early observations are already revealing active galactic nuclei at unexpected luminosities in the first billion years, adding data to the puzzle. But the answer is not yet complete. You are inside the puzzle. You are inside the universe that produced these objects, in the epoch when the fastest growing black holes were at their most active, and the mechanism by which they assembled their extraordinary masses is the mechanism operating around you right now. You watch the accretion disk of this smaller quasar, 200 million solar masses, intense ultraviolet output, jets extending 50,000 light-years into the surrounding galaxy, and you recognize what you are seeing. Not just a bright object, a factory, a machine for converting gravitational potential energy into electromagnetic radiation, operating at an efficiency that no other known process approaches. The gas that falls into this disk will not become stars. It will not become planets. It will not become the raw material of future life. It will be converted at up to 42% efficiency into radiation that streams outward through the universe, ionizing hydrogen, heating the intergalactic medium, shaping the large-scale structure of the cosmos in ways that will persist for billions of years. The disk around you does this without pausing, without cooling, without the possibility of intervention. You move through the ionized halo of the host galaxy, the extended region of warm ionized gas that surrounds the main disk, extending hundreds of thousands of light-years from the center, maintained at temperatures of tens of thousands of Kelvin by the ultraviolet flux from the active nucleus. In this halo, star formation is suppressed. The gas is too warm to collapse. Molecular clouds require temperatures below roughly 20 Kelvin to begin the gravitational collapse that leads to star formation. At the temperatures maintained by quasar irradiation, the thermal pressure of the gas overwhelms gravity. The gas cannot cool fast enough to condense. The quasar is preventing the halo from becoming a star-forming region. AGN feedback in action. The galaxy is being regulated by its own center. There is an elegant and slightly uncomfortable symmetry in this. The black hole exists because the galaxy provided the gas to feed it. The galaxy's outer structure is suppressed because the black hole is feeding. The more actively the black hole accretes, the more powerfully it suppresses the conditions that might produce the next generation of stars. Eventually, the gas supply is exhausted, either consumed, heated to the point of escape, or locked in the stellar populations that formed before the AGN became active, and the accretion rate drops. The quasar fades. The galaxy, now gas-poor, settles into a quieter phase with a reduced star formation rate. And then, millions or hundreds of millions of years later, a merger brings new gas. The cycle begins again. Some galaxies go through multiple AGN phases over their lifetimes. The scars of each phase are visible in the structure of the galaxy, in the radiolobes, the enriched intergalactic medium, the stellar population that records when the star formation was interrupted and when it resumed. You are watching one phase, one cycle, one moment in a process that will repeat in various forms in various galaxies for billions of years to come. The merger that triggered this AGN event is still in progress. The satellite galaxy, 50,000 light years from the center of its host, currently threading through the outer stellar disk on its first pass, has already disturbed the outer gas reservoir. The tidal streams it has pulled from the host galaxy are visible as faint arcs of stars and gas extending millions of light years into the surrounding space, slowly dissipating, slowly mixing with the intergalactic medium. On its next pass, in approximately 400 million years, it will enter the inner galaxy. The AGN may be re-triggered then if it has faded in the interim. The merger will take perhaps 1 to 2 billion years to complete, the two systems gradually losing orbital energy through dynamical friction, the interaction of each system's dark matter halo with the gravitational field of the other, until they settle into a single merged galaxy. The merged galaxy will be larger, rounder, more elliptical in structure, the angular momentum of the two systems having been redistributed during the merger into a less organized configuration. The two central black holes will orbit each other. They will spiral inward as they lose energy through the same dynamical friction process, interacting with the surrounding stellar population, scattering stars from their vicinity, and losing energy in the process. Eventually, after millions to perhaps billions of years, they will approach each other closely enough that gravitational wave emission becomes significant. The two black holes will lose energy to gravitational waves, spiral together in an accelerating in-spiral, and merge. The gravitational wave signal from two supermassive black holes merging will be among the loudest events in the universe, at the low frequencies where pulsar timing arrays and future space-based interferometers are designed to detect. The merged black hole, a Kerr black hole with mass and spin determined by the properties of its progenitors, will recoil from the merger due to asymmetric gravitational wave emission. It may be displaced from the galactic center. It will find its way back over millions of years through interactions with the surrounding matter. And then it will sit at the center of the merged galaxy, waiting for the next supply of gas. You pull back from this galaxy, from this 200 million solar mass system in the middle of its merger-triggered AGN phase, and look outward at the broader universe of this epoch. The quasar era is near its peak. In every direction, at distances of billions of light years, there are active galactic nuclei in various stages of their activity. Some are at their brightest, accreting at or near the Eddington limit, their disks blazing, their jets carving through their host galaxies. Some are declining, their gas supplies diminishing, their accretion rates falling, their luminosities decreasing toward the Seyfert galaxy and low luminosity AGN classifications that will represent a less extreme but more common mode of nuclear activity. The universe is also forming stars at its historical maximum rate. The cosmic star formation rate, the total amount of stellar mass being produced per year per unit volume of the universe, peaks at approximately redshift 2, at roughly the same epoch as the peak quasar activity. This is not a coincidence. Both processes are driven by the same raw material, cold, dense molecular gas. The galaxies that are most vigorously forming stars are also, in many cases, the galaxies most likely to have active nuclei. Massive, gas-rich, merger-disturbed galaxies doing both things simultaneously, building stars in their outer regions and building their black holes in their centers, are called submillimeter galaxies, named for the wavelength at which their heated dust emission peaks. They are among the most luminous objects in the universe at this epoch, and many of them host quasars. The universe is building itself. Stars forming, black holes growing, galaxies assembling through mergers. The dark matter halos that contain them growing through the hierarchical assembly of smaller structures. All of it happening at once. All of it powered ultimately by gravity, the weakest of the four fundamental forces, operating across the largest scales, inexorably pulling matter together, converting the smooth distribution of the early universe into the complex structured cosmos that will eventually produce the conditions for rocky planets, oceans, atmosphere, and the particular chemistry of life. You are in the middle of that process. Not the beginning, not the end, the middle, the peak of activity, the maximum brightness, the moment when the universe is most energetically productive. It will be quieter from here. Not immediately. The decline is slow. The quasar era does not end abruptly. It fades over billions of years, the active fraction of massive galaxies declining steadily as the gas supply is depleted, as the large merger rate falls, as the universe expands, and the average distance between galaxies increases, as the conditions that produced such abundant quasar activity gradually give way to the quieter universe of the present day. But the trajectory is set. From here, from the peak, the universe begins its long descent toward the contemporary quiet. You hold this in mind as you move. The next direction of travel is not outward in space. It is inward in time. Not backward, not further into the past, forward, toward the contemporary universe. Toward the universe that exists around the planet where you are lying, in the dark, listening to this. Toward the question of what happened to all of this brightness. Where the energy went. What the universe looks like now, 2 billion light years closer to home, at the place where 3C273's light will one day arrive and be caught by a Dutch astronomer's spectrograph on a winter night in California. The filaments of the cosmic web stretch ahead of you, the threads of dark matter and gas connecting the nodes of galaxy clusters across the immensity of space. You follow them forward, into the quieting, into the present. The quasars behind you are still blazing. They will be blazing for millions of years more. Their light is traveling toward you even now, toward the planet you came from, toward the telescopes that are pointed at the sky, toward the photographic plates and CCD detectors that are recording the universe as it was at this epoch from that distance. You are traveling in the opposite direction, back toward the planet, back toward the contemporary universe, back toward the question of what the black holes became when the quasar era ended. The galaxy clusters ahead thin as you move. The average separation between galaxies increases, the expansion of the universe, carrying all of them apart from each other, slowly diluting the large-scale structure, making mergers less frequent, reducing the rate of AGN triggering. The star formation rate falls. The AGN fraction falls. the universe dims. Not in any single moment, not as a catastrophe or a crisis, simply as the natural consequence of finite resources being consumed at a finite rate. The gas that existed in the early universe is being converted to stars, to stellar remnants, to the hot intracluster medium of galaxy clusters, to the warm hot intergalactic medium that fills the cosmic filaments. The reservoir is being drawn down. The universe becomes what it is. You move through it. The galaxies around you are more recognizable now, more like the galaxies you know from images taken by telescopes pointed at the nearby universe. Spiral structure is more common. The merger rate is lower. The fraction of galaxies with bright active nuclei is a small percentage rather than a large one. Some of those active nuclei are still quasars, technically. The distinction between a quasar and a lower luminosity AGN is partly definitional. Quasars are simply AGN above a certain luminosity threshold. As the peak luminosity of AGN in the universe decreases over cosmic time, the boundary between what counts as a quasar and what counts as a Seyfert galaxy or a low luminosity AGN shifts. The objects themselves exist on a continuum. There is no clean line. Just a continuous distribution of black holes, accreting at various rates, producing various luminosities, all of them the same kind of object, a supermassive black hole with an accretion disk, operating at different points in their activity cycles. In the contemporary universe, you are approaching, most of the most massive black holes are quiet. The one at the center of the Milky Way. The one at the center of the Andromeda Galaxy. The one at the center of M87, the giant elliptical galaxy in the Virgo cluster, whose black hole was the first to be directly imaged by the Event Horizon Telescope. These black holes are not gone. They are not different in kind from the objects you have been observing. They are the same objects in a later phase with less fuel. M87's black hole, 6.5 billion solar masses, the mass measured from the gravitational influence on surrounding stars and from the size of its shadow in the Event Horizon Telescope image, was once a quasar. It is not a quasar now. Its accretion rate is approximately 1,000th of its Eddington luminosity. Its jets are still present. M87 has one of the most well-studied jets in the nearby universe, extending 5,000 light-years from the nucleus, visible in radio, optical, and X-ray wavelengths, but they are far lower power than the jets of the classical radio quasars of the active era. M87 is in a maintenance phase, accreting slowly from the hot gas that fills the center of the Virgo cluster, not building mass rapidly, not ionizing a surrounding bubble of intergalactic hydrogen, not outshining its host galaxy by a factor of hundreds, just existing, a remnant of a brighter time. The Fermi bubbles of the Milky Way tell a similar story. Two lobes of gamma-ray emitting plasma extending 25,000 light-years above and below the galactic plane, symmetric around Sagittarius A*. They were discovered in 2010 using the Fermi Gamma-Ray Space Telescope, and their origin has been debated since. The leading interpretation involves a past period of AGN activity, a time when Sagittarius A* was accreting at a much higher rate than it does today, driving jets that inflated the bubbles over millions of years. That activity has ended. Sagittarius A* is now accreting at approximately 10 millionths of its Eddington luminosity. Its luminosity is roughly 40 solar luminosities. The Sun produces one solar luminosity. The object at the center of the Milky Way, a black hole of 4.15 million solar masses, is producing the luminosity of 40 suns. It is, by any measure, dormant. The contrast with 3C 273, which you left behind, producing luminosity equivalent to 4 trillion suns, is a factor of 100 billion. Same type of object, same fundamental physics, different fuel supply. You are close to home now. The galaxy clusters around you are recognizable. The large-scale structure of the contemporary universe, the filaments and voids of the large-scale structure, mapped in exquisite detail by galaxy redshift surveys like the Sloan Digital Sky Survey and its successors, is the structure you are moving through. The Virgo cluster is ahead, the nearest large galaxy cluster to the Milky Way, approximately 54 million light-years away, containing over 1,300 galaxies, dominated by the giant elliptical M87 with its sleeping 5 billion solar mass black hole. You pass it at a distance. The cluster is dense by cosmic standards, hundreds of galaxies within a region a few million light-years across, but still vast compared to any human scale. The galaxies are separated by hundreds of thousands of light-years on average. The hot intracluster medium, plasma at temperatures of tens of millions of Kelvin, pervading the space between the galaxies, glows in X-rays, detectable by space telescopes like Chandra and XMM Newton. Inside the intracluster medium, embedded in the deep gravitational potential of the cluster, the galaxies orbit slowly. Their black holes are quiet. The quasar era has ended here. You continue past the Virgo cluster, through the local supercluster, the Laniakea supercluster, a structure 520 million light-years across, containing the Milky Way and hundreds of thousands of other galaxies, and into the final approach. The Milky Way is ahead. Not visible yet as a distinct object, at this scale it is simply one galaxy among many, a single node in the local group of galaxies, its spiral structure indistinguishable at this distance from the spiral structure of any other disk galaxy. But you know it is there. And at its center, at the position of Sagittarius A*, the 15 million solar mass black hole that sits at the center of the galaxy where you were born, the story of the quasar era arrives at its contemporary expression. The same physics, running quietly. In the dark, you descend toward it. The galaxy resolves around you as you approach, the disk 100,000 light-years across, its 4 major spiral arms winding outward from the central bar. The bulge at the center a thickening of stars and dust, the halo of globular clusters and dark matter, extending hundreds of thousands of light-years beyond the disk. The interstellar medium of the Milky Way is complex, molecular clouds where new stars are forming, supernova remnants where massive stars have recently ended, the warm ionized medium of HII regions around young stars, the hot coronal gas of the halo. You move through it, toward the center. The star density increases as you approach the bulge. The stars here are old, most of them formed in the first few billion years of the galaxy's life, enriched by multiple generations of supernovae, red and orange in color, their hydrogen-burning years mostly behind them. The galactic center region, the inner few hundred light-years, is a different environment from the outer disk. The radiation field is more intense from the dense stellar population. The magnetic field is stronger, the gas more turbulent, the chemistry of the interstellar medium shaped by proximity to the central mass concentration. And at the very center, inside the central parsec, inside the region where the gravitational influence of the black hole dominates, there is a cluster of young stars, the S-stars. A group of massive young stars, some of them only a few million years old, orbiting Sagittarius A*, at distances of a few thousand astronomical units. Their orbits have been tracked over decades by the Keck Observatory and the Very Large Telescope, their positions measured year by year, their trajectories built up observation by observation. The orbits are Keplerian. They follow the same equations that describe planetary orbits in the solar system, but scaled up enormously and centered on the gravitational mass of Sagittarius A* itself. The star designated S2, the most closely monitored, has an orbital period of approximately 16 years and a closest approach to Sagittarius A* of approximately 120 astronomical units. At that closest approach, it moves at nearly 3% of the speed of light. Its orbit has been measured precisely enough to confirm the predictions of general relativity, the gravitational redshift of its light as it climbs out of the black hole's gravitational well, the precession of its orbit due to relativistic effects. Einstein's equations, operating at the center of the Milky Way, confirmed by watching a single star move. You watch S2 on its orbit. It is currently in the approaching phase of its 16-year cycle, moving toward its closest point. In a few years of its orbit, a moment by cosmic standards, it will pass closest to the black hole, its velocity peaking, its light maximally redshifted by the gravitational field. Sagittarius A* will not respond dramatically. There will be some increase in X-ray emission, perhaps, as the increased stellar wind from S2 at closest approach provides a slightly denser medium for the accretion flow, but no dramatic brightening, no quasar-level activation. The fuel provided by a single star's wind is vastly insufficient to drive the black hole into a high accretion state. In 2013 and 2014, astronomers tracked a gas cloud designated G2 as it approached Sagittarius A* on an orbit that brought it within a few hundred astronomical units of the event horizon. Predictions were made. Some hoped for a dramatic fireworks display, a brief reactivation of the galactic center AGN as the cloud was disrupted and accreted. G2 passed through periapsis. It was stretched by tidal forces. Some of its mass was dispersed into the accretion flow. Sagittarius A* barely noticed. The accretion rate increased marginally. The X-ray emission brightened slightly and briefly. Then it returned to its quiescent baseline. The black hole at the center of the Milky Way requires a great deal more fuel than a single gas cloud to wake up. For now, it sleeps. You are close enough now to see it. Not the black hole itself, the event horizon of Sagittarius A* has a Schwarzschild radius of approximately 12 million kilometers. At the distance of the Earth, that subtends an angle of approximately 50 microarcseconds, the angle resolved by the Event Horizon Telescope in its 2022 imaging campaign, the baseline of which spanned the entire diameter of the Earth. You are much closer than the Earth. But the event horizon is still invisible in the conventional sense, not because it is too small, But because a black hole emits nothing, the information you have about its location comes from its gravitational influence on the stars around it, from the accretion flow that surrounds it, from the photon ring, the bright ring of photons on circular orbits at 1.5 times the Schwarzschild radius that the Event Horizon Telescope imaged. You see the photon ring, a bright, thin loop of light, not emitted by the black hole, but emitted by the accretion flow and bent into a ring by the extreme curvature of spacetime near the event horizon. The ring is not perfectly uniform. The side of the ring where the accretion flow rotates toward you is Doppler brightened. The side rotating away is dimmed. The asymmetry carries information about the rotation of the black hole. You are seeing this structure now from inside the galaxy at a distance of a few light hours from the event horizon. It is quieter than 3C 273. Enormously quieter. The accretion flow around Sagittarius A** is radiatively inefficient. The plasma is so thin that it cannot cool effectively, and most of the gravitational energy of the infalling material is carried into the black hole rather than being radiated outward. The dominant accretion mode is called RIF, radiatively inefficient accretion flow, and it produces the faint flickering X-ray and infrared emission that characterizes Sagittarius A** in its quiescent state. There are flares. Occasionally, a few times per day, the X-ray emission from Sagittarius A** brightens by a factor of a few to tens, lasting minutes to an hour before returning to baseline. The mechanism is not fully understood. Magnetic field reconnection events near the innermost accretion flow are the leading explanation. Brief releases of stored magnetic energy that accelerate electrons to relativistic speeds, producing enhanced synchrotron and inverse Compton emission. The flares are gentle by cosmic standards. You watch one. A brief brightening of the inner accretion region, the photon ring flickering, the emission peaking in the near-infrared and X-ray, the energy output increasing by a factor of perhaps 10 for a few minutes, then fading. A sigh, and then quiet again. This is what the center of the Milky Way is now. A gentle flicker where once, millions of years ago, when the Fermi bubbles were being inflated, there was a sustained roar. The transition from active to quiescent is not unique to Sagittarius A**. It is the story of the universe's most massive black holes in the contemporary epoch, the Milky Way, Andromeda, M87, the thousands of giant elliptical galaxies in nearby clusters. Each of them hosts a supermassive black hole. Each of those black holes is in a low accretion, low luminosity state. The quasar era is not gone. It is archived. A code in the structure of the galaxies those black holes shaped, in the temperature of the intracluster medium, still hot from the AGN activity of the active era, in the chemical enrichment of the intergalactic medium, seeded by the stellar winds and supernovae that the quasars triggered and disrupted. In the mass of the black holes themselves, each one a record of everything it consumed in the active phase. The universe keeps records, not in books, in matter, in mass, in the slow cooling of gas clouds that were heated a billion years ago and have not yet had time to cool to the temperatures at which they would collapse and form new stars. In the orbital velocities of stars at the centers of galaxies where the black hole's gravitational influence is still the dominant force, billions of years after the quasar faded. The brightness is gone. The consequences remain. You are at the center of the Milky Way, watching Sagittarius A** flicker quietly in the infrared, surrounded by the S-stars on their long elliptical orbits, the galactic center molecular zone extending hundreds of light years around you, the rest of the galaxy, its 400 billion stars, its spiral arms, its gas and dust and dark matter, arranged around this quiet center like a city arranged around an old and sleeping monument. And you think of 3C273, 2 billion light years away, still blazing. The light that left 3C273 2 billion years ago is still traveling. Right now, at this moment, that light is approximately 2 billion light years from its source, approximately 0 light years from a small blue planet in the outer spiral arm of an ordinary galaxy. Some of it is arriving at Earth's surface tonight. Some of it passed through the atmosphere hours ago and has been absorbed by the ground, its energy converted to a tiny amount of heat. Some of it passed through the lens of a telescope in the Chilean desert and was focused onto a detector and will be recorded in a data archive that will eventually be analyzed by an astronomer who will publish a paper about the variability of 3C273's accretion disk. The light does not know any of this. It simply travels, as light does, at exactly 299,792,458 meters per second through the vacuum since the moment it was produced at the surface of an accretion disk surrounding a 900 million solar mass black hole 2 billion years ago in a galaxy that looks unremarkable from the outside. The universe does not announce its extraordinary events. They happen. The light travels. Someone eventually measures it. You are in the galaxy where the measurement was made. At the center of the galaxy where the measurement was made. Watching the quiet black hole that will never be as bright as the one whose light crossed 2 billion light years to be measured. Both of them real. Both of them the same kind of thing. One sleeping, one blazing, and 2 billion light years of dark between them, full of the light of a million other galaxies, the cosmic web threading through the void, the background hum of a universe that began 13.8 billion years ago and has not yet finished becoming whatever it is becoming. You rest here, at the center of things, in the quiet. The stars of the galactic center, the dense population of old red stars, the young S-stars on their eccentric orbits, the stellar remnants and neutron stars and stellar mass black holes that populate the central parsec, continue their motions. Everything continues. The universe does not pause for any observer, not even one who has traveled from a quasar 2 billion light years away, to arrive at the center of their own galaxy and sit with the quietly flickering black hole in the dark. But you can pause. You are pausing now. The breath is slower than it was at the beginning. The distances you have traveled tonight, the 2 billion light years to 3C273, the billions of years backward in time to the peak of the quasar era, the journey forward through the quieting universe to the contemporary Milky Way, those distances do not need to be held actively in mind. They are simply where you have been. You do not need to hold them. Let them be there. The photon ring of Sagittarius A** flickers once, gently, in the infrared. The S-star designated S2 continues its arc toward closest approach. The galactic center molecular zone hums with chemistry, carbon monoxide, water, formaldehyde, ethanol, dozens of organic molecules rotating in the millimeter wave background, building blocks of complexity in the cold, dense gas between the stars. The rest of the galaxy turns slowly around this center. One complete revolution for the Sun takes approximately 225 million years. In the time since the dinosaurs became extinct, 66 million years ago, the solar system has completed less than a third of one orbit of the galactic center. In the time since the last common ancestor of all life on Earth, roughly 3.8 billion years ago, the solar system has completed approximately 17 orbits. The galaxy has been turning since before life began on the planet where you are lying. It will continue turning long after any life that could observe it has come and gone. This is not a melancholy fact. It is simply the scale of the thing you are a part of. The Quasar era was real. It happened. Its consequences are embedded in the universe that produced you, in the temperature of the gas, in the mass of the black holes, in the distribution of heavy elements that made planets, and eventually chemistry, and eventually everything. You are a consequence of the Quasar era. Not directly, not in any simple causal chain you could trace, but in the same way that the contemporary universe is a consequence of the Quasar era, shaped by the feedback, enriched by the metals, structured by the heating and cooling cycles, driven by AGN activity. You are a product of a universe that passed through that phase. Everything you are is downstream of what you saw tonight. The black hole at the center of the Milky Way flickers once more. Soft, barely there, and the galactic center is quiet, and the stars continue their slow orbit, and you are here, in the middle of all of it. Exactly where you were when you began, you are still at the center of the Milky Way. The galactic center molecular zone extends around you, dense, cold clouds of gas and dust, threaded with magnetic fields, populated by molecular species that should not exist in such proximity to a source of intense radiation, carbon monoxide, hydrogen cyanide, ammonia, complex organics that form on the surfaces of dust grains in the cold, dark interiors of the clouds, shielded from the ultraviolet flux of the central stellar population by the dust itself. The clouds are named Skr B2, Skr C, the brick, the three little pigs. Astronomers, working with data from radio telescopes and infrared observatories, have mapped their velocities, their temperatures, their chemical inventories. Some of them are forming stars. Not many, and not rapidly. The central molecular zone has a star formation rate far lower than its gas mass would predict if it were a normal region of the galaxy. The reason is not fully understood. Turbulence, magnetic support, tidal disruption from the gravitational field of the galactic center, all of these have been proposed, and all of them likely contribute. But stars are forming. New stars, at the center of a galaxy whose central black hole once drove jets powerful enough to inflate the Fermi bubbles. The violence and the gentleness coexist here. They always have. You have been thinking about the past, about 3C 273, 2 billion light years away, about the quasar era, about the universe that existed before the contemporary quiet. Now, for a time, you will think about the future. Not the far future, not the heat death, or the big rip, or the evaporation of black holes by Hawking radiation. Those timescales are so far beyond human intuition that they require a different kind of patience than the one you are practicing tonight. The near future, the future that is close enough to be described by processes already underway. The nearest large galaxy to the Milky Way is the Andromeda Galaxy, also known as M31. Its distance is approximately 2.537 million light-years. It is approaching. The Milky Way and Andromeda are gravitationally bound. Their mutual gravitational attraction exceeds the effect of cosmic expansion at this scale, and the two galaxies are moving toward each other at approximately 110 kilometers per second along the line of sight. They are also moving transversely. The precise transverse velocity has been measured by the Hubble Space Telescope and by the Gaia mission, and the most current models of the merger trajectory suggest that the two galaxies will begin their first close passage in approximately 4.5 billion years. The merger will take several billion years to complete. The precise trajectory of any individual star, including the Sun, through the merger is not predictable with precision. The dynamics are chaotic at the level of individual stellar orbits. What can be predicted is the statistical behavior of the stellar populations. The most likely outcome for the solar system is that it will be displaced from its current position in the outer Milky Way to a much larger orbital radius in the merged galaxy, flung outward by the gravitational perturbations of the encounter, and will continue to orbit the center of the merged system at a greater distance than it currently orbits the Milky Way's center. The merged galaxy will not be a spiral galaxy. The angular momenta of the Milky Way and Andromeda are not aligned in a way that would produce a stable merged disk. The merger will produce an elliptical galaxy, a roughly spheroidal system of stars without the organized rotation and spiral structure of the parent galaxies. This merged galaxy has a name already: Milkomeda, or Milkdromeda. The two central black holes, Sagittarius A*, with its 4.15 million solar masses, and the Andromeda central black hole, M31*, with an estimated mass of approximately 100 million solar masses, will sink toward the center of the merged galaxy through dynamical friction. They will begin to orbit each other. A binary black hole system at the center of Milkomeda, slowly spiraling inward as orbital energy is carried away by interactions with surrounding stars. The so-called final parsec problem, the theoretical challenge of explaining how two black holes that have approached to within a parsec of each other can lose enough energy to merge on a timescale shorter than the age of the universe. The mechanism involves scattering of stars from the binary's orbit, each interaction transferring a small amount of energy from the binary to the scattered star, gradually hardening the orbit. For sufficiently massive binaries in sufficiently gas-rich or triaxially symmetric stellar systems, the process can proceed on timescales of millions to hundreds of millions of years. Once the two black holes approach to within roughly a milliparsec of each other, approximately 200 astronomical units, gravitational wave emission becomes the dominant energy loss mechanism. The inspiral accelerates. The orbital period decreases from years to months to weeks to days to hours to minutes. the amplitude of the gravitational waves increases. And at some moment, a moment that will occur billions of years in the future, long after the sun has expanded into a red giant and then collapsed into a white dwarf, long after the Earth's surface has been sterilized, the two black holes will merge. The event will last a fraction of a second in the frame of the merging black holes. The gravitational wave burst produced by a merger of the two galactic center black holes, Sagittarius A*, and the far more massive M31*, will be the most energetic gravitational wave event in the local universe in billions of years. It will propagate outward at the speed of light. It will reach the edge of the observable universe long after the expansion of the universe has carried all other galaxies beyond the cosmological horizon. The merged black hole, a Kerr black hole with a mass approaching 105 million solar masses, spinning rapidly, recoiling from the merger due to asymmetric gravitational wave emission, will settle at the center of Milky Way. And then, it will wait. The merged galaxy will have consumed most of its gas in the starburst triggered by the merger. The star formation rate will decline. The merger-driven infall of gas to the center, which may briefly reignite the Milky Way central black hole into a quasar-level active phase, blazing with a brightness not seen in this corner of the universe since the quasar era, will also decline. The quasar, if it ignites, will be brief by cosmic standards. Tens of millions of years. Then the gas is gone, and the center of Milky Way is quiet again. A sleeping black hole, the successor to Sagittarius A*, larger by a factor of 25. Otherwise the same, a Kerr black hole at the center of an aging elliptical galaxy, accreting at a radiatively inefficient rate, flickering occasionally in X-rays and infrared, its past embedded in the structure of the galaxy around it. The same story. At the next scale up, the future of the universe beyond the Milky Way Andromeda merger is a story told in decreasing energy. Not darkness, not immediately, and not in any abrupt sense. The stars will continue to burn, the universe will continue to expand. Galaxy clusters, bound together by gravity, will persist as isolated islands in an increasingly empty cosmos as the accelerating expansion of space carries unbound galaxies beyond the cosmological horizon. But the rate of new star formation will fall. The molecular gas that forms stars is being consumed. Some of it becomes stellar remnants, white dwarfs, neutron stars, black holes. Some of it is heated by supernovae and AGN activity and ejected from galaxies into the intergalactic medium, where it cools too slowly to be recycled on any accessible timescale. The reservoir is finite. The process of depletion is irreversible in the short term. In 10 billion years, the star formation rate of the universe will be a small fraction of what it is today. In 100 billion years, even smaller. The most massive stars, which burn through their fuel in millions of years, will be long gone. The intermediate mass stars, the ones like the Sun, will also have completed their life cycles, having swelled into red giants, shed their outer envelopes as planetary nebulae, and cooled into white dwarfs. What will remain, burning, will be the smallest stars. Red dwarfs? Stars with masses between roughly 8% and 50% of the Sun's mass. They are the most common type of star in the universe, Approximately 75% of all stars are red dwarfs. They are also the most long-lived. A red dwarf, with a mass of 10% of the Sun's mass, will burn hydrogen for approximately 10 trillion years, 1,000 times the current age of the universe. In 100 billion years, when the universe has passed through several more times its current age, red dwarfs will be the dominant luminous objects in the sky. The universe will not be dark. It will be dim, red, slow. And in the centers of the ancient, gas-depleted galaxies of that future universe, the black holes will still be there. Sagittarius A*, grown by mergers into the 100 million solar mass black hole at the center of Milky Way, will still be there, accreting perhaps at the trickle rate that a gas-poor, star formation-depleted galaxy can provide. Or dormant, waiting. The mass is not lost. Black holes do not evaporate on cosmological timescales. The Hawking radiation process, by which black holes slowly radiate energy due to quantum effects at the event horizon, is extraordinarily slow for massive black holes. The evaporation timescale for a black hole of 1 solar mass is approximately 10 circumflex 67 years. For a black hole of 1 million solar masses, the exponent scales with the cube of the mass, and the timescale becomes incomprehensibly large, far beyond 10 circumflex 80 years, far beyond any timescale associated with current cosmological processes. The black holes will outlast the stars. They will outlast the white dwarfs, which cool over trillions of years from the temperature of a stellar remnant to something approaching the temperature of the surrounding space. They will outlast the neutron stars. They will outlast almost everything. In the very far future, the era of cosmology that physicists call the degenerate era, spanning roughly 10 circumflex 15 to 10 circumflex 40 years from now, the universe will be populated primarily by stellar remnants, white dwarfs cooling toward black dwarfs, neutron stars spinning slowly down as they lose energy to magnetic dipole radiation, and black holes. The black holes will be the most massive objects in this era, the most energetically significant, the last engines, and eventually, over timescales that make the current age of the universe look like a single morning, they too will fade, not through Hawking radiation in any practical sense for the most massive ones, but through the slow processes of a universe that has exhausted almost everything else. The universe does not end dramatically. It dims. The same way a quasar dims, not in an explosion, not in a collapse, but in the slow falling off of fuel supply, the gradual decrease of accretion rate, the transition from brilliance to quiet. The universe's arc from the quasar era to the present quiet is the universe's arc written small, brightest in the middle, quieter toward the ends. And right now at 13.8 billion years in the contemporary epoch, you are in the quieting phase, not at the peak, past the peak, in the long, gradual, still luminous descent from the maximum brightness of the quasar era toward whatever the universe eventually becomes. This is not a diminishment. A quasar is not more real than a quiet galaxy. The Milky Way in its contemporary serenity, its 400 billion stars, its molecular clouds forming new solar systems, its red dwarfs burning patiently for trillions of years, is as real and as complete as 3C273 at peak luminosity, The universe at different phases of its history is not the universe at different degrees of value. It is simply the universe at different moments. You are in one of those moments. A moment of relative quiet compared to the quasar era. A moment of extraordinary complexity compared to the smooth, nearly featureless early universe. A moment balanced between the brightness that came before and the long cooling that comes after. Here, now, in this galaxy, on this planet, in this room, you sit with this future for a moment. Not with anxiety. These events are billions of years away in a universe that will be unrecognizable by the time they occur, populated by forms of matter and energy that cannot be predicted in detail from the current state of physics, but with a kind of clear-eyed recognition. The processes you have been observing tonight, the accretion, the jets, the feedback, the merger, the dormancy, the reignition, these are not historical phenomena. They are ongoing. They are the fundamental dynamics of the universe operating at the largest scales, and they will continue to operate long after everything that is familiar about the current universe has changed. The black hole at the center of the Milky Way was once a quasar. It will one day be part of a larger black hole. That larger black hole will one day, perhaps, be a quasar for a time. And then it will be quiet again. The universe cycles through these phases not because it is designed to, but because the physics of gravity and gas and radiation at these scales produces these outcomes inevitably, given mass, given angular momentum, given a finite supply of accreting material. The outcome is determined. The quasar is not an aberration. It is what a supermassive black hole looks like when it is fed. You have seen it fed. You have also seen it quiet. Both states are real. Both states are part of the same object at different moments in its history. The 900 million solar mass black hole at the center of 3C273 is not categorically different from Sagittarius A*. It is Sagittarius A** with more gas. It is Sagittarius A** in a younger universe, in a galaxy with more merger activity, in an epoch when the raw material for black hole feeding was more abundant. Given those conditions, Sagittarius A** would be 3C273. In different conditions, in a gas-poor post-merger contemporary galaxy, 3C273's black hole will be something very much like Sagittarius A*. They are the same thing, at different moments in the same story. The orbital period of the S-star S2, continuing its loop around Sagittarius A*, is 16.05 years, precise to 2 decimal places. The orbit has been measured for long enough, since the early 1990s, continuously improving in precision with better adaptive optics systems and longer baselines, that the orbital parameters are known to extraordinary accuracy. The mass of Sagittarius A** is known to within a fraction of a percent. The distance from the Sun to the galactic center, the fundamental parameter of Milky Way cartography, has been pinned down by the S-star orbits to approximately 26,700 light-years. The universe is measurable. This is worth pausing on. The orbital period of a star around a black hole, 4 million times the mass of the Sun, 26,700 light-years away, is known to 2 decimal places. The mass of that black hole is known to within a few percent. The distance from Earth to that black hole is known to within a few hundred light years out of 26,700. These numbers were not given, they were earned by decades of observation, by nights spent at telescopes in Chile and Hawaii, by the development of adaptive optics systems that compensate for atmospheric turbulence, by measuring and correcting wavefront distortions in real time, by the patient accumulation of data points that, taken together, trace out an orbit that confirms general relativity operating in the strong field regime at the center of our own galaxy. The universe does not announce itself. It yields its structure to measurement, and measurement requires patience. The same patience you are practicing now. S2 continues its arc. Squora asterisk flickers once, softly in the infrared. The galactic center molecular zone continues its slow chemistry, and the galaxy turns. You will leave the galactic center now. Not abruptly, there is no urgency, but the story has arrived at its resting point, at the quiet center of the Milky Way, at the sleeping black hole that is the contemporary expression of the same process that produced 3C273, and the remaining distance to travel is not across space. It is inward. You move outward from the galactic center, through the bulge, through the transition zone where the bulge stellar population gives way to the thinner stellar density of the inner disk. The spiral arms emerge around you as you move outward, not as sharp boundaries, but as regions of enhanced star formation and gas density, wound loosely around the galactic center in the trailing configuration that differential rotation produces over hundreds of millions of years. The Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the Orion spur, the minor arm, the partial structure, the local feature of the galaxy in which the sun sits, not a major arm, a small concentration of star-forming regions and young stellar associations embedded in the disk between the Sagittarius arm and the Perseus arm. The sun is in here, a G-type main sequence star, approximately 4.6 billion years old, approximately halfway through its hydrogen-burning lifetime, orbiting the galactic center at approximately 220 kilometers per second, at a distance of approximately 26,700 light-years from Sagittarius A*, one star among 400 billion. Nothing remarkable about it from the perspective of stellar physics, its mass, its temperature, its luminosity, all within the ordinary range of main sequence stars. It will continue fusing hydrogen in its core for approximately another 5 billion years before exhausting its fuel and expanding into a red giant. Its third planet, at a distance of 1 astronomical unit, carries on its surface a thin layer of chemistry complex enough to have produced organisms that can measure the orbital period of stars around black holes to 2 decimal places. That is remarkable. Not because it was inevitable, not because the universe aimed at it, but because, given 13.8 billion years of physics operating on the initial conditions of the Big Bang, producing stars, heavy elements, quasars, feedback, galaxy mergers, quiet black holes, spiral arms, star-forming regions, planetary systems. This outcome is among the things that happened. The quasar era happened. The reionization happened. The star formation happened. The solar system formed from a molecular cloud enriched by multiple generations of stellar nucleosynthesis, carbon, nitrogen, oxygen, iron, all of the elements heavier than hydrogen and helium, forged in stellar cores and dispersed by stellar winds and supernovae over billions of years. The chemistry happened, and here you are, a product of the same universe that produced 3C 273, not separate from it, not observing it from outside. Inside it, part of it, the light from 3C 273 that arrived at Earth tonight, the photons that traveled 2 billion years from the accretion disk of a 900 million solar mass black hole, will continue to travel after passing through Earth's atmosphere. Some of them were absorbed by the atmosphere, some struck the ground. Some passed through a telescope and were recorded on a detector. And some, a tiny fraction, an infinitesimal number of photons from a source 2 billion light years away, passed through the window of a room, through the glass, into the dark interior, and are here, right now. The light of a quasar is in the room with you. Not metaphorically, not as a figure of speech. 3C 273 is bright enough. Its apparent magnitude is approximately 12.9 in the visible, that its light is present in any location on Earth's surface that is not in complete darkness, mixed indistinguishably with the light of the moon and the stars in the glow of the atmosphere. The photons that traveled 2 billion years are here. They have arrived. Their journey is complete, and you are at the end of it. The room is quiet. The darkness is ordinary, not the darkness between galaxies, not the darkness at the boundary of the observable universe, not the theoretical darkness inside the event horizon of a black hole, but the ordinary darkness of a room at night, full of air at roughly 293 Kelvin, full of the sound of a building settling, full of the barely perceptible sounds of the world outside. The galaxy is turning outside. Sagittarius A** is flickering quietly at the center, 26,700 light years away. 3C 273 is blazing 2 billion light years in the direction of the constellation Virgo. The cosmic microwave background, the remnant radiation of the Big Bang, cooled to 2.725 Kelvin by 13.8 billion years of cosmic expansion, is arriving from every direction simultaneously, passing through the walls, through the ceiling, through you, carrying information about the state of the universe 380,000 years after it began. None of this requires your attention. It is simply happening, as it has been happening since before the Earth formed, as it will continue to happen long after the sun exhausts its fuel. You do not need to hold any of it. It holds itself. The breath slows. The body, which has been lying still through all of this, through the journey to 3C 273, through the descent into the accretion disk, through the transit of the jet, through the backward travel in time to the quasar era, through the approach to the early universe, through the return to the contemporary Milky Way, through the consideration of the future merger of the Milky Way and Andromeda. The body has been here the entire time. Still. Supported. The surface beneath you is real. The weight of your body against it is real. The temperature of the air is real. These things are as real as the event horizon of Sagittarius A** and the synchrotron emission of 3C 273's jet, and the orbital period of the S** S2. They are all part of the same universe, operating at different scales. The scale you are currently at, the scale of a body, a room, a planet, is not less real for being smaller than a quasar. It is simply the scale that is relevant to you right now. And right now, what is relevant is rest. The breath moves slowly. In, a pause. Out, a longer pause. The darkness is comfortable. The stars outside are still there, even if you cannot see them. The sun is below the horizon, the sky is dark, and if you were outside and looking up, you would see several thousand stars with the naked eye, a small sampling of the 400 billion stars in the Milky Way, the nearest of them 4 light years away, the furthest of the naked eye stars, several thousand light years distant. All of them burning, all of them fusing hydrogen into helium in their cores, releasing energy through the mass-energy equivalence that Einstein described. The same fundamental process that powers the sun, the same process that operates at 60 times lower efficiency than a quasar accretion disk in every star you have ever seen. The stars are patient. They burn for billions of years without interruption, steadily, at the rate determined by the balance between the inward pressure of gravity and the outward pressure of radiation from the nuclear reactions in their cores. You do not need to match that timescale. You only need tonight. The breath continues. The body is heavy in the way that bodies become heavy when the muscles release and the nervous system settles into the condition it finds most natural, the condition of rest that evolution has been calibrating for hundreds of millions of years across every vertebrate lineage, built into the architecture of the nervous system as deeply as any other feature. You are doing what you are built to do. The darkness continues. The quasar is 2 billion light years away. The black hole at the center of the Milky Way is 26,700 light years away. The nearest star is 4 light years away. You are here. That is the relevant distance tonight. The breath is slower now than it was a few minutes ago. This is normal. This is the body doing exactly what it is designed to do when lying in the dark with nothing requiring immediate response, reducing metabolic rate, reducing heart rate, reducing the frequency and amplitude of the neural oscillations that characterize wakefulness, beginning the transition toward the slower oscillations that characterize the early stages of sleep. The body knows how to do this. It has been doing it for your entire life. It does not need instructions. It only needs the absence of interference. You are providing that. The room is still. Outside, if you were listening for it, you would hear the very faint sound of wind, or traffic, or the settling of the building, or the ambient hum of electronics, the ordinary background of existence on the surface of a planet with an atmosphere and a civilization. These sounds do not require interpretation. They are simply the texture of the present moment. The galaxy turns. Not noticeably, not from 1 minute to the next. The galactic rotation period of the solar system is 225 million years, and in the span of a night, the change in position is measured in thousands of kilometers, imperceptible against the scale of the galaxy. But the turning is real. And the quasar, in the direction of Virgo, is real. And the light that left it 2 billion years ago, which has been traveling through the expanding universe since before multicellular life existed on Earth, is still arriving. It arrives tonight. It arrives every night. Patient, continuous, indifferent to whether anyone is measuring it. The Orion Spur, where the sun sits, is approximately 3,500 light-years wide and roughly 10,000 light-years long. Within it, scattered along the local arm structure, are several well-known star-forming regions. The Orion Nebula, 1,344 light-years away. The Eagle Nebula, 7,000 light-years away, home of the Pillars of Creation, imaged by the Hubble Space Telescope, and later revisited by the James Webb Space Telescope, in near-infrared wavelengths that penetrate the dust to reveal the young stellar objects embedded within. The Carina Nebula, 7,500 light-years away, a region of intense star formation and stellar feedback. In all of these places, gas is collapsing. New stars are forming right now, in this moment, from molecular clouds that have been slowly accumulating density over millions of years, triggered by the compression of a nearby supernova shockwave, or by the gravitational perturbation of a passing spiral arm density wave, or simply by the slow accretion of material until the gene's mass is reached, the threshold at which the thermal pressure of the cloud can no longer resist its own gravity. The gene's mass depends on temperature and density. Cold, dense clouds collapse more easily than warm, diffuse ones. The molecular clouds in the Orion Nebula have temperatures of roughly 10 to 30 Kelvin in their densest cores. The gas is extremely cold, and in those cold, dark cores, regions so dense that even the interstellar radiation field cannot penetrate, regions where the only light is the faint infrared glow of the dust grains themselves, protostars are forming. Objects that will become stars have already begun their gravitational collapse. They are not yet fusing hydrogen, they are not yet on the main sequence, they are still accreting mass from the surrounding envelope, their internal temperatures not yet high enough to ignite the proton-proton chain or the CNO cycle that will eventually provide the pressure to halt the collapse. But they are on their way. In perhaps 100,000 years, an instant by stellar timescales, some of them will ignite. New stars in the Orion Nebula forming right now while you rest. The universe is not finished building itself. It is still in the middle of the process, past the peak of its star formation rate, yes, but still producing new stars, new planetary systems, new chemical environments in which the processes that led to you might be occurring in other forms, around other stars, in other places in this galaxy, and in the 2 trillion other galaxies that populate the observable universe. 2 trillion. The revised estimate of the number of galaxies in the observable universe, derived from deep field surveys conducted by the Hubble Space Telescope and corrected for the faint galaxies that are below detection threshold, is approximately 2 trillion. Most of them contain supermassive black holes at their centers. Most of those black holes are currently quiet. Some fraction of them are active. In the observable universe right now, in the universe as it exists in the present epoch, not as it was in the quasar era, there are active galactic nuclei at various luminosities, from the modest Seyfert galaxies visible in the nearby universe, to the rare, bright quasars still found at high redshift, the last representatives of the great active era burning through the remaining gas supply of their host galaxies. Each one is the same fundamental object: a black hole, feeding. The diversity of observed AGN phenomena the Seyfert galaxies, the radio galaxies, the blazars, the radio-quiet quasars, the narrow line and broad line AGN, the low ionization, nuclear emission line regions, is largely explained by a unified model in which all of these objects are the same thing viewed from different angles and at different accretion rates. The orientation of the accretion disk relative to the line of sight determines whether the broad emission lines of the rapidly orbiting inner accretion region are visible or obscured by the surrounding torus of dust and gas. The accretion rate determines the luminosity. The jet orientation determines whether the object appears as a radio galaxy or a blazar. One object, many appearances. The universe is not as complicated as its catalog suggests. Its fundamental objects are few: particles, forces, fields. From those, everything, every quasar, every galaxy, every molecular cloud, every protostar, every rocky planet with an ocean and an atmosphere and a thin film of chemistry is assembled. The simplicity at the bottom and the complexity at the top are both real, both part of the same universe, the one you are resting in. The breath is slower than when you started. The body is heavier in the way that a resting body becomes heavy, not with effort, but with release. The galactic center is 26,700 light-years away. 3C273 is 2 billion light-years away. The cosmic microwave background is arriving from every direction, as it always has. The Orion Nebula, 1,344 light-years away, is forming new stars. S2 continues its orbit around Sagittarius A*. Andromeda is 2.537 million light-years away, approaching at 110 kilometers per second. All of this is happening. All of it will continue to happen. None of it needs anything from you tonight. The universe does not require your attention to continue. It simply continues, as it has for 13.8 billion years, as it will for whatever duration remains ahead of it, whether the universe is open and expands forever, or whether some currently unknown physics eventually halts or reverses the expansion, or whether the dark energy that drives the current accelerating expansion eventually tears apart the large-scale structure of the cosmos in a Big Rip scenario billions of years hence. The universe continues, and tonight you rest inside it. The breath moves in, out, slower. The distance between each breath is a little longer than the last. This is fine. This is correct. The nervous system is doing what it does. Sagittarius A* is doing what it does. 3C273 is doing what it does. The cosmic microwave background is arriving from every direction, as it has been arriving since the universe first became transparent 13.8 billion years ago, and as it will continue to arrive for trillions of years to come, growing cooler with each passing epoch as the expansion of the universe stretches its photons to ever longer wavelengths. Right now, its temperature is 2.725 Kelvin. In a trillion years, it will be 0.000027 Kelvin. The universe cools slowly. There is no hurry. There has never been a hurry. There is one more measurement worth knowing before sleep takes over completely. The Hubble constant, The rate at which the universe is expanding is currently measured at approximately 70 kilometers per second per megaparsec, depending on the method used. This means that for every megaparsec of distance between 2 points in the universe, approximately 3.26 million light-years, those 2 points are moving apart at approximately 70 kilometers per second due to the expansion of space. The Andromeda Galaxy, despite its approach, is an exception. It is close enough that gravity overcomes expansion, but beyond a certain distance, the Hubble radius, approximately 14 billion light-years, galaxies are receding faster than the speed of light, not because they are moving through space faster than light, but because space itself is expanding between us. Those galaxies are already beyond our cosmological horizon. We can never receive a signal from them. We can never reach them. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is all we have access to. Everything outside it is in principle forever unreachable. The quasar 3C Docientas Setenta y Tres is inside the observable universe. Its light reaches us. The universe that produced it, the accretion disk that powered it, the jet that extends 3 million light-years from its nucleus, all of it is accessible to measurement, to observation, to the slow accumulation of understanding that science is built from. This accessibility is not guaranteed. As the universe expands, more and more galaxies will cross the cosmological horizon. In approximately 2 trillion years, the only galaxies visible to any observer in the Milky Way, or Milkomeda by then, will be those gravitationally bound to the local group. Everything else will have receded beyond detection. An observer in that future universe, without access to the accumulated records of the current era of astronomy, would have no way of knowing that the universe contains 2 trillion galaxies. They would see only a handful. They would measure an expansion rate, but without the deep field surveys of the contemporary era, they would not know whether their small visible universe was typical or exceptional. They would not know about quasars. They would not know about the reionization epoch. They would not know about the cosmic microwave background in its current form. By then, it will have redshifted to wavelengths so long they lie beyond any practical detection. The window for measuring the full structure of the universe is open now. It will not always be open. The observations being made in the current era by the Hubble Space Telescope, by the James Webb Space Telescope, by the Vera Rubin Observatory, by the Event Horizon Telescope, by pulsar timing arrays, listening for gravitational waves from supermassive black hole binaries. These observations are not being made at an arbitrary time. They are being made at the moment in the universe's history when the full scope of the cosmos is still visible. When the quasar era is recent enough to be studied in detail. When the cosmic microwave background is still detectable. When the structure of the observable universe, the filaments, the voids, the galaxy clusters, the distribution of matter across billions of light-years can still be mapped. This moment will not last forever. It is long by human standards, short by cosmic ones. And in it, on a small planet in an unremarkable galaxy, the universe is being measured and recorded and understood piece by piece, observation by observation, the structure of a cosmos that began in a point and expanded for 13.8 billion years into everything you have visited tonight, becoming available to the understanding of the beings it produced. The universe made something that can know it. Whatever else is true about the cosmos, that is true. The breath moves. The body rests. The quasar blazes. The black hole at the center of the Milky Way flickers, once softly in the infrared. And you are here, in the dark, in the quiet, in the middle of a universe that has been producing extraordinary things: quasars, reionization, galaxy mergers, the slow enrichment of the interstellar medium with heavy elements, the formation of planetary systems, the emergence of chemistry complex enough to produce organisms that can wonder about quasars since before the Earth existed. You are one of those extraordinary things. Not the brightest, not the most energetic, but here, aware, resting. That is enough. That has always been enough. The stars continue outside. The galaxy continues. The light continues to travel. And you rest here in the room in the dark, on the surface of a small rocky planet in the outer spiral arm of a galaxy whose central black hole flickers quietly in the infrared, and whose future includes a merger with the Andromeda Galaxy and the production for a brief cosmic moment of a quasar that will be visible from neighboring galaxies before it too quiets down and goes dark and waits, patient in the way that black holes wait for the next supply of gas. All of it is happening. None of it requires your attention right now. Let it happen without you. The breath, in, out, the darkness, the quiet, the ongoing universe, doing what it does, while you do what you do, which is this, which is rest. If tonight carried you somewhere, if the journey to 3C 273, to the accretion disk, to the jet, to the early universe, to the galactic center, to the future merger of the Milky Way and Andromeda, gave you something to rest inside, this channel would be grateful for a like and for a subscription, and for the notification turned on so the next episode finds you when you need it. There are more places to go, more science waiting in the dark, more light that has been traveling for billions of years toward a small planet where someone is lying quietly, listening. We will go there together. But not tonight. Tonight is finished. Everything you heard tonight is real. A quasar is out there right now. Good night.